effect of X-rays a little bit on planets. What I really wanted to talk more about was that whole sea of things that planets go around and through. Mike said, whoops, let me activate that. The decadal theme here is, of course, worlds and suns in context, and that is to get at what Tansu just talked about, which was how stellar activity might affect the evolution and habitability of exoplanets. Mike asked me to talk about astrospheres, and I was trying to come up with a way to explain astrospheres and what is meant. And I went back to my youth a little bit and thought about how Obi-Wan Kenobi might have described an astrosphere. And that is, it's an energy field created by all stellar things, or at least all stellar things below about 2 solar masses, surrounds us, penetrates us, and it binds the system together. You have to understand that we right now are existing in an astrosphere, in the stellar wind that's coming from our sun. And this has implications, some of which Tansu sort of alluded to in his talks, that we call space weather. And at the moment, we are seeing the eroding of the atmosphere of Mars because it doesn't have a magnetic field and it's sitting in this astrosphere. I'm going to focus on the origin of the astrosphere in this talk, which comes from stars. And the key elements here are sunspots, which give rise to solar flares, which sometimes give rise to coronal mass ejections. And overall, these things give rise to the stellar wind. And it's that stellar wind that fills the volume of the astrosphere. So I'm going to take each of these in turn and put the whole thing together at the end, and hopefully it will make a little bit of sense. So starting with star spots, in general, star spots are optical phenomena like you see on the top of this figure over here, with little dark patches on a bright star. But underlying the optically dark regions are these X-ray bright regions shown in this image, which we've seen, if you look long enough, you can actually see these modulations. So in about 2004 or 5, we did a COOP survey of a little under 1 million second observation of the Orion star forming region. And Edre Filcomio and his collaborators were able to look through that data and to detect at least 23 stars that had periods in their X-ray modulation between about 2 and 12 days. And the amplitudes of these things were pretty big. They range from 20% to almost a factor of 2. And this is actually fairly tricky work because the stars are flaring underneath that. This is the sun, of course, but the light curves you see on the top are from the COOP survey. And what you see is a flare here and a couple flares over there. And we had to remove the flares, look at the remaining data. You could then do a periodogram analysis and you could see the peaks here and compare them to what was seen in the optical, and they matched up fairly well. And so this is clearly what we were seeing, but with the factor of 6 or so extra collecting area that we would get from AXIS, the noise here is going to go way down, and we should be able to carry out this experiment on many more than just 23 stars. Now, as these chromospheric hotspots move around, those become the roots of the stellar flares. As the magnetic fields bind through, you get the reconnection and the breaking of the magnetic field lines. And I'm not going to go through the whole standard model here. This is not a talk on stellar flares. That's 20 minutes in and of itself. What I want you to focus on here are the soft X-rays that are going to generate when these loops bind together and then break. We're going to see those. And then also this plasmoid here that can fill up with mass. And if there's a large plasmoid, when the flare occurs, that's going to break off, and that's going to be the thing that gives rise to the coronal mass ejection that we'll talk about in a few slides. So going back to the COOP study, what we're looking there is starting with sort of the basal flux and then moving on to the flares that arose from 1,000 stars. So what I'm showing you here is just sort of the inner 8 arc minutes, so 4 arc minutes off axis on either side of M42. There's about 800 or 900 stars in that image. And for Chandra, we could really only deal with this middle area right here. As you see, our PSF is degrading very quickly. And here's a part of the COOP field we don't show you very much, is we're about 7 arc minutes off axis out here. And you can see very clearly that the PSF is deteriorating, our signal to noise is going down, our sensitivity to these sources is plummeting. So with an instrument like AXIS, we can really catch the whole field. And remember, the Orion star forming region is not just M42. It goes all the way down the length of the sword, and it goes all the way up through the OMC 2-3 region. In our follow-up studies with XMM, we only gathered another few hundred stars as we went down the sword, because we were very much sensitivity limited. So first of all, an instrument like AXIS is going to allow us to get much deeper and a much more complete sampling of the whole of the Orion region. And then when you stare, this is what we saw. It almost looks like a Christmas tree sparkling. And what you're seeing here are all the flares that took place during the COOP observation. And it's not that every star is constantly flaring all the time. Each star is flaring only once or twice in this image, but it gives us impression of the constant flaring. On the other hand, it gave us examples of about 1,000 flares on 1,000 stars. Some were stronger, some were weaker. And then we can go in and look with the COOP. We were sort of limited to the brightest of these flares. This particular flare, for example, had 16,000 counts. And that allowed us to measure the temperature, the peak temperature of the flare, the temperature evolution of the star from the pre-flare to the post-flare condition down here. The emission measure, we also were able to get a measure, for example, of the magnetic field strength and the loop length. Now, we were only able to do this with a few dozen stars in the case of Orion, but with AXIS and its effective area and its very high spatial resolution, we'll be able to look at, sorry about that, we'll be able to look all the way to the Carina Nebula and Cygnus at about 2.5 kiloparsecs and get the level of detail you saw in that previous image for over a dozen star forming regions. And you know, this gives us access to planet formation environments that we're going to, over the course of the next 10 years, have a very good idea of the populations in terms of the protoplanets and planets of, because of follow-up missions like Plato and JWST. So we can do this for a big cluster, or we can stare at a specific interesting nearby planet hosting star and pull out this kind of information. So what I'm just showing here is what you can do with a larger sample. We went back about 10 years ago and looked through the entire Chandra catalog of flares, and we measured for about 24 flares the properties that included the loop length. Some of these loops reach into the inner part of the planetary system, the plasma temperatures, the plasma density. So we really are able to use the flares to get a measurement of what's going on outside of the star into that area where the planets exist. This is the base of the astrosphere. So I just wanted to stop very quickly and tell you where we are. We have, with our effective area of AXIS, we can reach time resolutions of tens of minutes to ones of minutes out to distances of 50 kiloparsecs. Sorry, yeah, 500 kiloparsecs. Yeah, parsecs. Sorry, switching topics. Out to the Orion Nebula, we can measure these light curves. With Chandra, we had resolutions of a few hours. With AXIS, we're going to have resolutions of a few minutes. Moving on to coronal mass ejections. These come from flares, but not every flare has a coronal mass ejection associated with it. So we can see these coronal mass ejections in the sun by direct observation, But in the X-ray, we're going to have to rely on indirect methods. And one of the best methods of these is coronal dimming. So I'm showing here is a nearby plan hosting star, Proxima Cen. Here is the basal flux level out here. And then there was a flare, and then the flux level dropped below the basal level. And then there's another couple of flares. And what's interesting is in the second case, you have a very small flare, a huge dimming, and then another flare, and the dimming actually begins to go away. But the dimming here gives you access to the amount of material between you and the star that you can directly measure. So now we're moving out into that astrosphere, and we're getting a measurement of the density of the material in it from the coronal mass ejection. I'm not familiar with whether or not AXIS is going to be carrying a UV detector. That might be something we could discuss in phase B. But if it does, it allows you access to the Neupert effect, which again will tell you if a particular flare is associated with the coronal mass ejection. You can then use some scaling laws, and this has been done by a few groups, including Jeremy Drake and Arnio and Rachel Austin and myself, where you can scale what you see on the sun to what you would be seeing from the exoplanet or see from any other star. Doesn't have to have an exoplanet around it. And these relationships tell you for a given X-ray flare, if you have an idea of you can measure directly the X-ray fluence, and then from there you can get an idea of what the mass or what the overall kinetic energy of that flare would be, and then that's filling up the astrosphere. Now this can be complicated by the magnetic topology of the star itself. That's another thing that AXIS is going to give us. AXIS is going to give us access to. I'll try to say that 3 times fast. Beyond the CMEs themselves, there's of course the CMEs come from the breaking of these field lines over here, but of course there are some open field lines over there, and that just gives you an overall solar wind. And what I'm showing you here are measurements of the solar wind from our star's stellar wind, what we call the solar wind. And then if a flare takes place, you'll get a burst of these electrons. And then later on, after the electron burst, you'll see protons that are traveling at a few thousand kilometers a second. So these protons are accompanied by high velocity nuclei of nitrogen and carbon and oxygen 7, oxygen 8. These measurements give us access directly to the stellar wind, the temperature of the stellar wind, and the velocity of the stellar wind. And these can be observed on stars. So what we see here is that in young stars, the ratio of the oxygen 8 to oxygen 7 seen in X-rays is fairly, it varies a little bit, but the luminosity of the overall oxygen line is fairly fixed. When you go to main sequence stars like the sun, the luminosity traces the ionization state that you're seeing. And this is, of course, what we're looking at when we're looking at the astrospheres of older stars. So now what I want you to imagine is you have this solar wind, you have this sea of ionized particles, and it collides with a neutral. And in this case, we're discussing neutrals that are going to come from comets. In the case of our sun, you would typically have one comet at a time, but in younger systems, you can have tens or hundreds of thousands of comets. And of course, the amount of neutral or ionized particles in more active systems can be higher. In the case of the sun, we see the neutrals interact with the high density and high velocity solar wind, and that gives rise to the X-rays. So the X-rays you see are a direct measurement of the stellar wind and can tell you something about the size of the interacting object. And so what we've seen here, there are a couple of examples that we've seen with both Rosat and Chandra. And these are big. These things are tens of thousands or hundreds of thousands of kilometers in extent. This one imaged by XMM Newton is gigantic, but it's under-resolved. Both XMM and Chandra lack the collecting area to actually resolve the structures in these comets down to their resolution capability. So really what we got were spectra. These are the spectra of a range of comets observed by Chandra. And what you notice here is that in some cases, the spectra are fairly soft. There's lots of emission here on the carbon side and not so much on the oxygen side. But in other cases, the oxygen goes up and the carbon goes down. And this has actually been traced to the solar wind. So if the solar wind or stellar wind is relatively cold and fast moving, you're going to see these kinds of spectra. And if the solar wind is relatively fast moving and hot, you'll see these kinds of spectra. This is the resolution that we will be getting with AXIS. And it didn't take long for Brad Wargelin and Jeremy Drake to figure out that if you had either a big solar wind or a lot of comets, that you would see an extension beyond the star of strictly the solar wind. So this is some work they did in 2004, focused specifically on Proxima Centauri. So for other objects, you'll have to scale. But basically what they saw was that a point source, the flux will go down fairly quickly. But if you have an extended halo emitting the stellar wind, emitting charge exchange, you should be able to resolve that. So could you? Well, we think we've done that. So this is a paper that Casey Lice and collaborators are finishing up. Maybe we'll submit it this month, I'm not sure. What we're doing here is we're comparing the point spread function that we saw with a couple of young stars and this third star here, HD 61005. This star is about 35 parsecs away. It's about a little under 100 million years old. And what we see is that for Beta Hydrae and Tau Ceti, the end of the PSF is at about 2 pixels from the center of the star, whereas for HD 61005, we don't actually get down to 0 until you get to about 7 pixels from the star. So it seems to be extended. Is it really extended? Well, what we did was we compared the central region of the star to the outer region of the star. And the central region over here, we see silicon-13, magnesium-11, neon-10. Basically, this looks like a hot corona at about 6.5 megakelvin. But if we looked at just the photons in that outer edge, they look very different. They're very much shifted to the soft end. There's this huge neon 9 line, or what looks like a neon 9 line. There's a neon 7 or oxygen 7 signature. This looks like charge exchange. So it looks like what we've seen is a star in the middle, and then charge exchange on the outside. And this would be, we think, the first detection of an astrosphere. And this is where AXIS can help, because really what we're trying to, whoops, sorry about that. Really what we're trying to identify here is, the charge exchange signature. We can't identify which kind of comet we're seeing in the red right now, but if we had that extra factor of 6 collecting area, we could. So I'm gonna finish there. AXIS will basically improve all levels of access we have to astrospheres. I just realized my camera was off. And the excellent spatial resolution will allow us to detect all young stars, basically out to 2 kiloparsecs, with time resolution on the order of minutes. This will allow us to actually make longitudinal maps of the hot spots, the star spots on these stars, which we could then map to what planet they're in front of. And we can go all the way down to the origins of the stellar winds, and we can resolve these structures with AXIS for any star that has them out to about 30 or 50 parsecs. So I'll stop there. Thank you.
Great, thanks, Scott. That was a really good talk. So do we have questions? We have 5 minutes here, so if people want to raise their hands, give people a moment. Go ahead, Damien.
Hey, Scott, can you go back to your figure for 61005? Is that ACES or was that the HRC?
Okay, so this is ACES observations right now. We're going back, we just got observations last week with XMM. Now, XMM doesn't resolve the astrosphere. So with XMM, what we're hoping is to be able to figure out if there are two spectra here. But the spectra will totally overlap. So we'll just be able to more or less put together, is it a soft plus a hard thing? And does the soft thing not look like thermal? So this is, where access would be so much better, because then we'd be able to sort of separate out the photons that we want to look at.
But for ACES, you're sort of stuck above 500 EV right now, or?
Yeah, so another observation that was just approved is to go back with HRC. And HRC will get down to 200 EV. But again, this is the problem. Right now, we have to sort of go to XMM for one thing, ACES for another thing, HRC for a third thing, and each of them is missing an aspect we need. So HRC will really get pristine imaging, but it won't be able to have any spectral resolution. So just know, we'll confirm the extent, we'll confirm how much it's extended, but then we have to go back to the ACES data and say, okay, are the spectra really different of the two things?
And HRC is working well again? Is that true?
It will, yeah, the only limitation for HRC right now is the time of individual exposures is limited. So we might have to do 2 or 3 observations to add up to the total amount of exposure time we want.
And what is the low end for AXIS? What's the softest energy?
Mike, is it 200 EV, 250?
Yeah, it's 200. Yeah, for the CP.
Yeah, and so that really gets into this whole sea of lines right over here.
Yeah, there's a lot down there. Yeah.
Okay, are there other questions? If there are, raise your hand. I'll ask one question as well. So thinking about that kind of like Christmas tree, flickering that you see from all the flares, when we're kind of connecting that back to exoplanets, I mean, the flares.
Yeah, so it's complicated. So each one of those flares can be a good day and it can be a bad day. It's a good day if you have a primordial atmosphere and you're trying to clear that stuff out, because when the Earth forms, it has this huge atmosphere of hydrogen and helium, and it's got to lose that somehow. So it's really the CMEs that do the work, because the CMEs have the mass to push things out. So the key thing here is the X-rays are telling us more than just about the X-rays. The X-rays are telling us about the matter that's also coming out in those high energies. And so the good day comes when the matter, the kinetic energy comes through and it clears out all that overlying mass. Now the bad day comes when that's already happened and you're beginning to develop what they call the secondary atmosphere, the carbon dioxide, carbon monoxide, and all the outgassing from the interior gases. And maybe you've got some creepy crawly on the surface, and then another one of those things comes by. And that can reset your biological clock over and over again. And I think that's one of the things we want to look at. So each of these flares you're seeing right now could have been a good day or a bad day for life on that planet. As we get later along the chain and you're in Proxima Centauri, you still have a fairly active star that's not a mature corona. That corona is still flaring. And that's one of the things we've been seeing, is that some of these, especially close in exoplanet systems, has this ability to produce these long-lived and long-length flares that could lead to a bad day.
Okay, great. Yeah, that's such a cool image to see the flickering like that. That's awesome. So yeah, it is. They